This is actually a summarized version of one of my PV pressure vessels and piping conference tutorials that ran for 4 hours, which was a summarized version of our one-day brittle fracture workshop. So there's going to be a lot of details that we'll be missing, but we'll try to cover as much as we can. Just about me, I have over 17 years of industry experience in various roles as inspector, piping design engineer, and stress analyst, fracture mechanics analyst, and do a lot of pressure vessel design and piping design, fitness for service analysis. Just a disclaimer here, I will talk about the code aspects at some level in this webinar, but all of those should be taken as my opinion and not as an opinion of ASME or Stress Engineering Services. So the outline for the presentation today is basically we're going to talk about some of the nomenclature and how does the auto-refrigeration affected the industry with some examples of events, and briefly discuss about the brittle fracture basics and the parameter that has been used quite a bit to characterize the fracture resistance. And we'll also delve into the details of the code aspects of the brittle fracture prevention and how does post-construction codes address the brittle fracture prevention. There's one important term that is essential to this discussion, which is a critical exposure temperature, which goes along with the process hazard analysis. We'll discuss in that briefly. I wouldn't be touching a lot of details on PHA today because that's a whole new topic that had to be discussed separately. We'll talk about some example scenarios and we'll go through some example brittle fracture assessments that will be beneficial to the audience. We'll have some closing remarks at the end. So first things first, nomenclature. What is auto-refrigeration? So these are all things that get encompassed in what's called as the Joule-Thomson effect, which is essentially an adiabatic expansion. In proper terms, auto-refrigeration is the unintentional and uncontrolled phase change from liquid to a vapor of a hydrocarbon that results in refrigeration. This is the refrigeration which, when you don't want it, you get it, and you get it when you least expect it and when you're not controlling it. And brittle fracture is the sudden and often catastrophic fracture of a material with little or no plastic deformation. Relatively low levels of energy required to initiate or propagate a flaw. In a sense, for all brittle fracture assessments, the initiation is assumed to be complete. That is, there's always an assumption that a flaw is present. And also, brittle fracture is a rapid crack propagation phenomena through the material and will result in leak. And the leak can result in explosion if there is a hydrocarbon involved and flammable hydrocarbon involved and a source of ignition. This is unlike the other mechanism, which is a leak before break. It's the opposite here, break before leak. In some materials, the crack speed approaches the speed of sound of the material, so you can imagine how fast the fracture can be. Critical exposure temperature, it is defined widely across various standards, but it is the lowest temperature experienced by the piece of equipment as a result of auto-refrigeration, Joule-Thomson effect, exposure to cold liquid that's not designed for exposure. Low ambient temperature can also be considered a critical exposure temperature in certain scenarios. Minimum allowable temperature is the lowest temperature allowed at a coincident pressure to ensure the vessel remains ductile. We'll talk about the brittle and ductile in a little bit. MAWP, most of you know, is the maximum allowable working pressure. It's based on code allowable stresses. Minimum design metal temperature or the MDMT, is a code-specified value by owner, developed by owner, or value determined as part of code design. And, for example, if you go to ASME Section 8 Division 1, UCS 66 rules would apply unless UG 20 rules apply. It also equals the MAT at the MAWP, the lowest temperature allowed at MAWP to ensure the vessel remains ductile. Post-well heat treatment, everybody knows about this. This is to reduce the residual stresses. Minimum pressurization temperature is often used by the reliability personnel to look at the manageable envelope, safe operating envelope. The other item related to the MPT is MSOT, minimum safe operating temperature. We'll discuss this in later slides. I would like to get into the industry events that emphasize the importance of the auto-refrigeration and brittle fracture. One of the major incidents is the Moore's exchange failure that involved 2 people getting killed and 7 burned and 5 disabled. We'll talk about that in detail. And the other incident is Lake Charles flare drum failure. Fortunately, this did not result in any injuries. Longford exchanger failure. That one is another major one. It had, in addition to people getting killed, it had a huge economic impact. Beringen is in Belgium. It's a HDPE plant that had a failure in 1998, and this is at a flange, and this issue is still being discussed widely across the industry because of the nature of the material that caused this failure. Many of the flanges that has been supplied since for over a decade or more have issues with regard to toughness. So this one was the first incident to that effect that is widely known. Westlake flare piping, we'll talk about that too later in this presentation. And then there are numerous other hydrotest-based brittle fractures that occur every year. As I mentioned, some of these will be discussed at some length. So Mars exchange failure, this was in the news. This is a newspaper shot, and let's look at what happened exactly. So Mars was trying to start back up after a fire incident, and what happened was that this particular heat exchanger inlet flange had a leak. In order to stop the leak, this valve was closed. This is a overhead valve, and ethylene started accumulating in this drum. And while they were working to resolve the issue, this particular valve was leaking, and ethylene was at a very low temperature, was making this particular heat exchanger cold. So when the plant started back up, the pressure increased, and the low temperature of the material induced brittleness, and the high pressure resulted in this explosive failure. So this was the remains of that particular heat exchanger. So once again, to emphasize the incidents, it never occurs during normal operation. So we call that an excursion. Normally, those are not the things that are designed, although the code has evolved to address some of those unconsidered cases in the design in the recent days. A process upset of some sort is often the initiator for all these events. Subsequent actions by operators can also cause the chain of events to progress to a much higher consequence. The risk of brittle fracture is transitory, with potential only occurring within a window of vulnerability. Often this window passes without notice. Doing the wrong thing during the vulnerability window can be catastrophic. Let's talk about some brittle fracture basics. Brittle fracture can be characterized just like in the case of a fire triangle with a triangle. Some authors prefer to use quadrilateral. However, these are the 3 initiators or the 3 sides of this element. One is the crack or the presence of a notch and a sufficiently applied stress usually the code varies in terms of, as you look through the codes, the number varies from 6 KSI through 8 KSI, which is actually considered the primary stress that would cause a brittle fracture. So if you operate below that stress, then you're not closing this side of the triangle, because typically the presence of a crack or notch is always considered as present. The susceptible steel, this is where the material behavior comes into picture, whether the material behaves brittle or ductile. We'll go into that in a little bit. So the same material can behave ductile at a higher temperature and can behave in a brittle manner at a lower temperature. So this is a curve they call the toughness versus ductility transition curve. And this particular location on this curve is referred to as the nil ductility temperature location. So this plot is between what's called as the fracture toughness, or which is a measure of absorbed energy in fracture, versus the temperature. So as you can see, a material can go to a brittle phase if the temperature goes lower. Brittle materials almost exhibit no energy absorption during the propagation of crack, but the ductile materials, when external work is applied, it gets partly accumulated by plastic deformation or strain hardening. So more stable crack growth in those cases. Every time a material gets cold, especially carbon steels, it is of concern because of this behavior. So what is toughness? Depending on the level of academic interest, it can be defined in various ways. In general, it represents the resistance of fracture and is measured by the absorbed energy up to the fracture. Fracture toughness, for most of the fracture mechanics analysis involving single parameter crack driving, fracture toughness is a property indicative of a material's resistance to fracture when a crack is present. However, there is another parameter that's being widely considered and being researched over several decades. It's called T-stress, which addresses the constraint effect. We're not going to talk about that, although the codes are addressing that at this time. Typically, this fracture toughness is represented by the term K1C. There are K2Cs and K3Cs. We're not interested in that for this discussion because this mode of failure is the most common mode of failure. And also this fracture toughness is determined by using the following tests primarily in the order of their expense. The cheaper test is the notch toughness. The typical one is Sharpie V-notch. It is not a direct measure of toughness, although there are correlations that exist that give a clear indication of where the toughness is. There is CTOD testing, also known as crack tip opening displacement testing, and then J1C testing and K1C testing. We have to also look at the effect of thickness when considering the fracture toughness. For many years, the thickness effect was not considered in the codes. If you look at this graph, we know that the nil ductility temperature, or the transition brittle to ductile transition temperature, is somewhere here. For a common thin section carbon steel material, the brittle to ductile transition temperature is about -20 degrees Fahrenheit. Although for the same material, if the thickness is higher, the curve gets shifted to a warmer temperature. And this is one of the reasons why many of the failures were noticed in thicker sections. And also, this is the primary reason why in high pressure vessel designs, the fracture mechanics approach is involved. In 1981, the Section 8 group formed a task group to address the effect of this thickness, which eventually resulted in the current exemption curves involving the function of thickness. Those were implemented in 1987 in the code. Let's look at the effect of nickel on the transition temperature. We know that the nil ductility temperature is somewhere here, and you can see that the addition of nickel certainly helps in reducing that nil ductility temperature. as we go higher nickel. So this is a colorful edition of the previous slide with more materials, and you can notice that the stainless steels do not exhibit this nil ductility temperature transition. Let's look at the processes that are subject to potential auto-refrigeration and brittle fracture. The plants that need to consider are primarily the olefin plants, gas processing plants, refineries, polymer units, ammonia units, and any light liquid processing units that process C4 to C1 liquids. The primary mechanism here is the adiabatic expansion, so topside gas processing also need to consider this. So how does the ARBF prevention program elements look like? So you have to form a team, and then you have to identify the vessels that may subject to auto-refrigeration, and then execute a brittle fracture analysis, which basically involves developing a MAT curve. And then you can take either the process approach, as shown on the left-hand side, or you can go to study the PHA study that involves developing more accurate CET calculations, and then you can look at the risks involved, and then you can track action items in the PHA tracking system. So for the most part, we're going to address in this presentation only up to this portion. We're not going to look into these other portions because of the time limitations we have for this webinar. So what does the toughness rules or the brittle fracture prevention rules say, or where do you find them in the codes? So the fracture toughness rules in various codes are given below. In the case of Section 8 Division 1 pressure vessels, it is given under UCS 66. Article M2 if you were to use a previous edition of Div 2, and Section 3.11 in Div 2 in the low 2007 edition, 7 and later editions. By the way, 2007 is the major rewrite edition for Division 2. Section 323 of B31.3 also covers the toughness rules. There's only minor differences between Section 81 and 31.3 rules. For the most part, they're the same. Section 4 in both API 620 and 650 storage tank codes. Typically, the storage tank brittle fracture or fracture toughness rules are more stringent than the other code rules. Essential elements of toughness rules are either mandating impact tests or an exemption from the impact test. So if you were to impact test something, then you can confidently place them in service for that particular service. However, exemption from impact tests, you refer to these exemption curves provided in the code, which we will address later. For post-construction purposes, for vessels that are in service or piping that are in service, we have the post-construction code such as API 579, specifically Part 3 or Section 3 of that standard addresses the brittle fracture prevention. Note that brittle fracture can be prevented. That's basically how the fitness for service is addressing this particular damage mechanism. Unlike other damage mechanisms, brittle fracture event will make or break. Generates, basically in this process, we generate a MAT curve, and it involves every component assessment in the pressure vessel or the piping. We're going to talk more about the 2A, the method 2A in this presentation. And MAT results are also used to compare the PHA developed CETs. And that's how we determine whether a vessel is at risk or not. Once again, API 579 flowchart of assessment. There are 3 levels of assessment. 2 levels are shown here. In the order of complexity, level 1 involves either impact test or the exemption of it. And level 2 has the 3 particular components or equipments in the assessment: pressure vessels and piping systems and storage tanks. Method A involves developing a safe pressure temperature envelope Method B involves hydrotest-based assessments. Method C is basically a proof test or basically a flowchart-based method. So in more detail, level 2 methods involve, in the method A, there are 3 options in level 2. Method A involves, so you can use either one of them alternatively. Method A involves some level of stress analysis, either using hand calculations for pressure vessels or using complex Caesar models or piping stress analysis software for piping. And method B, as I mentioned, it's based on hydrotest. Method C is using flowchart. For piping systems, a simplified flowchart is given on the right-hand side. So it goes through a logical process, and you determine whether you're at risk or not. The major modification that came in this flowchart was in 2016 when the CET was lowered, increased to -20 degrees Fahrenheit based on industry experience. Level 3 is based on fracture mechanics-based approaches and typically involve another section of API 579 using reference flaw approach. Currently, the code or the standard uses quarter T reference flaw, T being the thickness of the component being assessed. It might change in the future. And further reduction in MAT. So the MAT is the MAT that we talk about here is the MAT that is developed either based on impact test or exemption curves. We'll get to the exemption curves in a bit, but that MAT can be reduced further for taking credit for operating at a lower stress. So there are 2 stress ratios involved in this assessment. One is based on pressure, and the other one is based on stresses. And then you go to this equation that determines what is the final minimum allowable temperature. So on the right-hand side here is the graph that shows the temperature reduction for various allowable stress materials. So this is pretty apparent in the Part 3 assessment, and further credit can be taken for post-well heat treatment. So these are the exemption curves. So these exemption curves basically exempt, if you're falling in one of these curves, you don't need to do impact tests. So these curves were developed based, as you can see, these show governing plate thickness at the bottom and the minimum allowable temperature or the minimum design temperature, depending on which standard you're looking at on the vertical axis. So back in '81, so various materials were tested and operating experiences were also considered in developing these curves, which were smoothened by a correlation that involved some level of fracture mechanics of the day. So you can see that commonly used materials are falling in curve A or curve B. The other way to represent this exemption curve is this Sharpe transition curves. So what it says is that if you look at 15 foot-pound Sharpe energy, which is being considered as the transition nil ductility transition energy, if you look at that and you replot those exemption curves, then you will see that the reference temperature or the nil ductility temperature increases as you go higher in the curve. So, for example, the blue line here represents curve A, while the purple line here represents curve D. So as you go higher in the alphabet, then your nil ductility temperature or the ductility transition temperature increases. More incidents. These are some of the pictures that were taken from the API 571, and most of these failures were during hydrotest. And the reason we bring that is because, so this is the record of failures have been plotted here by by one of our colleagues, and he looked at the data over the years and he plotted against the exemption curve and then looked at which ones failed and what thicknesses have been failing. So if you look at the bottom of this graph, most of the failures are about half-inch thickness, and 2/3 of these failures, recorded failures, are during hydrotest. So basically, most of the failures that are still happening are in hydrotest. So let's go into the details of MAT curve. So what is a MAT curve? If you were to do a simple post-construction brittle fracture assessment for an excursion event for a particular pressure and temperature, the MAT is a single value. However, if the pressure varies and you want to consider the risk involved for a particular pressure vessel, which is operating at various pressures and is handling a particular olefin, then you need MAT curve. So basically on this curve, on this graph, the blue line shows the MAT curve and the red line shows the flash curve or the CET curve of the hydrocarbon or the olefin. So the flash curve basically indicates that if you're below that, you're in liquid phase, and if you're above that, you're in the gaseous phase. And if the MAT curve falls below this curve, you're inherently safe to operate. That is, failure is not predicted. So this is for one particular example of a material wall thickness and pressure that was considered, and the olefin the olefin considered for this particular example is propane. Just to recap how this is developed, you do the stress ratio calculation at each pressure, and then you do the temperature reduction at each stress ratio and plot and develop this plot of minimum allowable temperature. So one example would be looking at this. How is it applicable to the industry? So for example, this MAT curve is plotted for one particular vessel that's operating at 180 psi at 90 degrees Fahrenheit. And the operating medium here is propylene. And if you look at the flash curve, which is about the MAT curve in this case, and let's consider one scenario, which is a one-step auto-refrigeration, we call it. So you operate at a pressure, at a normal operation pressure, you depressurize it, and then you repressurize it at this pressure. The metal temperature remains the same. So the pressure increases, that means you're increasing the risk of brittle fracture. However, while the MAT curve is still below this horizontal line, then the risk is minimized. In the other scenario where you just go all the way and de-inventory, where the pressure goes all the way to zero, and then you restart, the metal temperature is very low at this point, and yet if you repressurize it, you're still above the MAT curve. So this is an inherently safe vessel, and this is how you would do a process safety or process hazard analysis. Let's look at another vessel. In this case, the medium is propylene. Once again, the operating pressure is 180 psi and the temperature is 90 Fahrenheit. And the MAT curve is a little different than the previous one, so this is a different vessel. Once again, if you're operating at this pressure and temperature, you're safe. And when you go along the flash curve and then you come back and you want to restart, once again, you're safe if it is rapid without returning to equilibrium. Our typical process restarts would involve a slowly returning to equilibrium scenario. And the process should place controls to consider these upset conditions, because if you go below 17 degrees Fahrenheit on this curve, and if you come, then you would intersect this MAT curve, which will put this vessel at risk. So critical exposure temperature, this is very essential to determine accurately. It is determined based on startup, which can be lowest one-day mean ambient temperature, normal operation temperature, shutdown, or any other upsets, or standby when not in operation. And it can be from hydro test as well, and also auto-refrigeration and other Joule-Thomson cooling mechanisms. Shock chilling is another one when you introduce cold fluid into the system to cool the system faster to restart. And these are determined using PHA, which is the process hazard analysis, or other comparable assessment methodologies. Typical hydrocarbon CETs from the flash curves are shown here, methane being the lowest temperature. Most of the methane services involve stainless steel anyway, and ethylene and ethane are the next vulnerable scenarios. So this is probably the repeat of the previous one slide I gave earlier. However, some points need to be considered here, which were not discussed earlier, because this is part of the PHA, so you have to consider the PHA techniques such as event tree, guide list, and black box. So these can be part of a next discussion that we may be able to provide. However, these are not discussed due to the time constraints. Once again, there are many tools available to determine the CETs. Sometimes it's easier to determine just using the flash curves, and also changing the mixture of the composition and determining it. Some of the tools that are available to determine the CETs are HISIS and a few other tools. In some cases, it is hard to determine that, so you may need to perform actual computational fluid dynamics analysis, such as this one here, where a relief valve is subject to depressurization scenario. So one example that would be applicable for a real life plant would be to look into an ethylene plant. The ethylene plant has a hot section where you have the quench primary fractionator, water quench, CO2, and hydrogen sulfide removal, and then you go to this colder section, which is after the refrigeration unit. The cold section here will have several towers, demethanizer, deethanizer, and C2 splitters and other de-olefinizers, basically. Now let's look at one particular. In some of the vessels, there may be different materials of construction from the bottom to the top, so you may need to develop different mat curves for each section. Let's look at one particular example here, one particular vessel. And this is operating. This is a drum that's operating at a pressure of 340 psig and a temperature of 0 F. Let's look at the mat curve for this vessel. In this case, it's the deethanizer reflux drum. There are two CET curves provided. One is for ethane and the other one is for ethylene. Ethylene having the lowest operating temperature, or the lowest CET. It is no coincidence, right? So you can see that the MAT from API 579 based assessment can only go to -155. And if you look at the ethylene's lowest CET, it is -152. Regardless, if you look at this one, this MAT curve, so you can see that for normal operation, which is this location right there, we are inherently safe. But if you depressurize, like in a two-step auto-refrigeration scenario, and then you bring it up, then we are at risk. So this is just illustrating how important it is to establish a MAT curve, and looking at it from the perspective of process hazard analysis. The essential reason why we are discussing this in more detail is that the most recent standards are pretty thorough, in the sense that most of these scenarios are being listed as potential brittle fracture scenarios. However, previous editions of the code do not list many of these scenarios or the excursions. and most of the pressure vessels operating at this time are or either put in service several decades ago. So let's look at one example. For example, in Section 8 Division 1, it did not include the serviceability under low temperature excursions such as auto-refrigeration until 1999. So the code included the thickness-induced effects in the exemption curves were introduced in '87. That was one major change, and then we had a little more changes coming in the following years. And B31.3 did not have many of those items listed in 2002 until 2002. However, the exemption curves were introduced earlier. Regardless, the toughness rules are used in developing safe operating envelope for pressure vessels, and then those curves are used to control or eliminate the process risk to prevent brittle fracture failures. In the case of ammonia bullets, like the one shown on here in this example, the auto-refrigeration and brittle fracture hazard is primarily a potential issue. And in this example, the primary objective is to address auto-refrigeration and brittle fracture hazards with the operation of the ammonia feed systems. So the material of construction is given here. This is a very old ammonia tank, ammonia bullet, and the thicknesses are of concern. As you can see, the thickness is greater than ½ inch for both shell and head. And the mat, if it were to be determined from the exemption curves, is 69. So you would have to develop the mat curve for this one, and then look at the flash curve for the ammonia and look at the risks from that standpoint. So the normal operating pressure and temperature is 138 psig ADF. If you repressurize it to the PSV set point, then the vessel is not at risk. However, if you go to a low temperature interlock where the pressure is 99 psi and the temperature is 65, you are at risk of brittle fracture. So it's just illustrating how important it is to develop mat curve and look at it from the standpoint of process hazard analysis when the vessel was not designed to address these concerns. So the other incident that happened was the Westlake flare piping incident. Fortunately, this one did not involve any failure. In hydrocarbon service, there has been several flare line ruptures. Therefore, it is something that each ethylene plant should review, particularly at every revamp or expansion. Once the flaring in this particular scenario, once the flaring of ethylene began, the cold flare drum here, the cold flare drum overhead line experienced low temperature at some point, and that low temperature was not recognized by faulty instrumentation. Now, this resulted in the failure, but the investigations done on the failed material indicated that the material did not meet the required Sharpie energy, and the failure was at an elbow, and elbows are typically highly stressed locations in a piping system. Regardless, the flaring is a common phenomena, and relieving is a common phenomena happening both in topsides and downstream and other operating facilities. So here, how do you address such a relieving scenario or a flaring scenario? So there's a PSV here. This is an example problem involving piping system, and then there's a downstream pipe. So in this case, the CET was established to be -100 degrees Fahrenheit, and you run it through the level 2 assessment procedure. And the easy assessment would be the method C, which involves the flow chart. However, this material was, even though it is thinner than ½ inch, it does not qualify through the method C. So one has to do either hydrotest-based assessment or stress analysis-based assessment. So using stress analysis, you can model the system and then and then come up with the stress ratios and temperature reductions. So once again, API 579 or the design standards say that you have to consider every component and look to see if every component passed the assessment. So every component in that system is listed here, and it is compared against the minimum metal temperature or the CET. And this is the original MDMT for that material. It is mostly impact tested, and then the reduced MAT based on the level 2 assessment is shown here. And for this example problem, this system passes because it is operating at a lower stress. Oftentimes, the reliability engineers would like to do analysis with MSOT or the minimum pressurization temperature. It is a safe operating envelope. It is easy to develop for pressure vessels. However, for piping systems, it is a little complex in that it involves a lot of iterations. Regardless, one such MSOT curve is shown, envelope is shown here. The flash curve for the medium is shown in this red line. And the vessel 1 safe operating envelope or minimum pressurization envelope is shown in this blue line, and for the other vessel, it is shown in the red line. The piping system that connects to both the systems is shown in various levels depending on what component is being assessed is shown here. For this particular system, if you look at it closely, the piping is not a concern, but the pressure vessel and the flash curve defines the safe operating zone. If you look at the graph closely, the pressure is plotted on the vertical axis and the temperature is plotted on the horizontal axis, which is actually the reverse of a MAT curve. This is very useful for the operators, so this is often considered as one of the tools. In some cases, when it is hard to establish the CET, you may need to perform computational fluid dynamics analysis to establish the metal temperature. And also, such assessments may involve invoking level 3 based brittle fracture assessment. For example, in this case, you can see that for the flange, for this valve's flange location, the temperature was very low, and low being minus 147 degrees Fahrenheit. This is in methane service, and Joule-Thomson effect was the reason during the relieving, and a reference law approach had to be invoked, which involved a level 3 Part 9 assessment as well. So the complexities are there. However, the solutions are provided in the standards to address any kind of complexity. Now, there's one other issue that I mentioned earlier regarding the Beringen, the Belgium plant flange failure that resulted in a lot of discussions across the industry about the forged flanges, the A105, for example, about their quality and usability. So there was this, there's a lot of studies out there. So this one example is where this one particular low toughness flange was being subjected to bolt preload and operational loads that, stemming from Caesar or piping stress-based analysis, and looked at the MAT curve based on the data available from Sharpie tests across the board. And the MAT curves were developed using pure fracture mechanics approach for various fracture toughnesses. So there's a lower bound, there's a median and upper bound, depending on the data available. And if you notice this for ethane, so there's a spectrum of flash curves here, propane being at the warmest section and ethane being at the ethylene is not included, that would be the lowest in this case, but ethane is a good example. However, if you look at it for one location in the flange, which is the crotch location here, it's hard to highlight it, but anyway, it's here. For that location, the MAT curves indicate a potential risk for brittle fracture. However, this assessment involved several conservatisms. So if one were to relax some of those conservatisms, it may bring down the MAT curves below at least one of these olefin CET curves. Care should be exercised when doing such analysis. However, for material quality reasons, uh, brittle fracture assessment shall be performed based on level 3 assessments. And that would be the end of the discussion, and the concluding remarks are presented here. Basically, we covered, do you have mats for all your equipment subject to auto refrigeration or brittle fracture? And have you utilized the equipment mats in your PHAs? And again, this is because most of the vessels in operation are old and may not have been designed based on most recent rules that that require one to include scenarios such as auto refrigeration or low ambient temperature. And the third bullet here, it's a real process. ARBF is a real process safety hazard and can have significant process safety risk. We covered the risks involved. We covered evaluating the vessels and piping for fitness for service using advanced methods. And we briefly touched PHAs and requiring detailed documentation of vessels, mats, and PHA findings. With that, I conclude my presentation, and thank you for being patient in listening to this conversation. I open this to any questions at this point.